The beginning of chapter 5 talks about estimating with finite sums. And what we're going to be estimating is the area under a curve, which is actually the second part of calculus. So we're going to look at the graph of 5 over x. And what we want to do is estimate the area under the curve from 1 to 5. And there's a couple of options for how we can do this. We have LRAM, RRAM, MRAM, and then using the trapezoid method. And I'm just going to walk you through all four options using the same function, so a lot of our numbers will hopefully be the same. So with LRAM, that's what we're going to do on this slide. We're going to use four rectangles from x equals 1 to x equals 5, and we're going to base our rectangles, or the height of our rectangles, on the left side. So if x equals 1 is right here, I want to use this point here to draw a rectangle. So maybe I'll use red for this. So I'm going to start right there and just kind of draw this rectangle right here. I'm going to use that to find the area of that section of the curve. And then for the next rectangle, there's the left side. Here's my third rectangle. There's my fourth rectangle. So you can see that all the heights are based on the left side of that partition of the different bases that we have for our four rectangles. And so this is going to be an overestimate of the entire area. But in the end, we are trying to estimate the area under the curve. So how should I do that? Well, if you notice, all the bases of the rectangle are 1, and I just need to worry about the height. So I'm going to make a little t-chart to show the y values that I'm interested in. So if I make my t-chart here, if I plug a 1 into the function, I get 5. I plug a 2 in, I get 2.5. Plug a 3 in, I get 1.6 repeating. And a 4, I get 1.25. And those are the different heights of my rectangle. So what I need to do then is calculate the area of each one. Again, we talked about how the bases are already a length of 1. But they won't always be. Sometimes they'll be a half or a third or 3. So I just to get the notation down, I want to take my height, oops, there we go, my height times the base. That'll give me the area of this first rectangle, 5 times 1. I'm going to add to that my next y value, which was 2.5. Again, my width was 1. That'll give me this area. Plus, my next height was 1.6 repeating times a base length of 1. That gets me the third rectangle, and then 1.25 times 1. That'll give me this next one here. And so then I would add all that together, and that's going to tell me what my estimated area is. And so when I add those all together, I get 10.417 square units, you could say. That's my estimated area under the curve. That's going to be LRAM for this one. And it looks like that's going to be an overestimate. So my question is, what would I have to do to use the same method but get a better overall estimate of this area? Okay, the next example is the same picture, but now we're going to do RRAM. So now I'm going to base all the rectangles, again, from x equals 1 to x equals 5, using the right-hand side of those rectangles. So for the rectangle that's going to fit, oops, I have my pen selected there, for the rectangle that's going to fit right here, I'm actually going to use this as my height. For the next one, I'm going to use the right, so we're using the right-hand side all the time for our different heights. And so again, I can make a t-chart. There's going to be some similarities in what I do. The bases of all my rectangles are still going to be 1, but I'm going to be using different heights, and it looks like my area would be an underestimate in this case because all the rectangles are fitting underneath that curve. And so now when I make my t-chart, I'm using a lot of the same y values, but instead of using x equals 1 at the beginning, I'm going to start with x equals 2, and I have to add x equals 5 way at the end. So I take 1 away, I add 1 to my chart. But the overall idea is going to be the same. Now I take my different heights. So my first one was 2.5, my base was 1. And again, I know multiplying by 1 is kind of redundant, but it does just kind of get that in your head that that's what you would do in case you did not have the base length of 1. Okay, but all these things are just finding the different areas of these rectangles. Okay, and I would add those together. I'll do that in a second. And in this case, when I add them together, I get 6.417. That is RRAM using the right-hand side of all these rectangles. And again, that's going to be an underestimate in this case. So the question has to be asked, what would I do to still use RRAM, but to get a better estimate of the area under the curve? That'll be something we talk about tomorrow. Okay, our third example here, again, the same graph. Now we're going to use something called MRAM. And in that case, we're going to look at each interval, and we're going to pick a y value that's right in the middle of it. So this one's a little bit more challenging, I would say. For the first little rectangle from x equals 1 to x equals 2, I want to think about what's going to happen at 1.5. So maybe the y value that I pick is, oops, I should be using red to stay consistent, right about there. So that's going to be the rectangle. And for the next part, it looks like it'll be somewhere right around there. That's going to be my rectangle. And right there. So again, just a different method. And now in this case, you can see that sometimes part of the rectangle is under the curve, sometimes it's over the curve. And so this one might be our best estimate so far, but it won't always work out that way. Don't assume that MRAM will be the best. But our t-chart will look a little different. We have to think about what we're plugging in. I'm plugging in a 1.5, 2.5, 3.5, and 4.5 to get these different y values, or these different heights to my rectangles. This is going to make it a little bit more challenging, perhaps a little bit more messy. And so you can see the numbers are a little messier here, the y values or the heights of our rectangles, but it still follows the same basic pattern. I'm going to take my different heights. So I'm going to take 3.3 repeating. So that was the height of this first rectangle right here. And then the base is still going to be 1. Again, it will not always be a base of 1. It just happens to work out nice this time. So I just found the area of these first two rectangles there. The next one would be 1.429. That's a 1.429 times a base of 1. That's going to give me this area. And a 1.1 repeating times 1, that'll give me the last one right there. Okay, I add those together. And when I do that, I get 7.873 square units. That's for MRAM. Again, it's just an estimate. It's not perfect. And so, same question. What would I have to do in this picture and in the first two that would get me a better estimate of the area under this curve from 1 to 5? And our last example, using the same function, same interval, now we're going to use trapezoids. So we have to think back to geometry a little bit and think about an area formula for a trapezoid. It's be a little bit trickier. In general, what we want to do is first draw in the trapezoid. So this is going to be one side of that trapezoid. The other one's going to be right here. And we just connect those two. So a trapezoid, remember, has two parallel sides, and then the other two can kind of do whatever. But you can already get a sense here maybe that this is going to be a much better estimate. And in general, I think it would be somewhat safe to say that for most of the times that we do this, if all the intervals and the number of shapes are the same, a trapezoid will be the best estimate of this area under a curve. Okay, so how do we find the area of these shapes? Remember that the area formula for a trapezoid is 1/2 times the sum of the two bases times the height. But that's when our trapezoid, when the parallel pieces are horizontal. So when it's flipped like this, we need to remember, if I look at the first trapezoid, that this is a base and this is a base, and that interval from x equals 1 to x equals 2 is actually our height. So it does get a little tricky, but that's basically the setup here. So we're going to do the same thing. You're going to notice that a lot of the bases in this case are going to be our y values, and the height will always be 1. So it's a little bit of a different sense than the rectangles, but we're going to use a lot of the same numbers. So again, I can make this t-chart that we've been using for quite a while. And so when I'm just going to make my t-chart sideways this time just to save a little bit of room. But now for every trapezoid, it's going to be a little bit more writing here. But for the first trapezoid, I'd say to do 1/2 times the sum of my two bases, so those are the y values now, so it's going to be 5 plus 2.5 times a height, in this case of 1. And then I would move on to the next trapezoid. So that's going to be, let's change colors here. Now I'm using the same base here and adding to it the base right there. So my height, or I'm sorry, my bases or my y values would be 2.5 and 1.6 repeating. And my overall height for the trapezoid, or you can say base from how we used it with rectangles, is 1. Okay, so that was how I found these two so far. For my third trapezoid, it's going to be 1/2. The bases in this case are 1.6 repeating and 1.25. And my height for that one was 1. And then my last one again is 1/2. Now it's going to be 1.25 plus a 1 for my bases and an overall height of 1. So those last two got me these two parts. So you see there's going to be a little pattern here. It's a little bit more work to write out, but there is a pattern. The first y value and the last y value you're going to end up using once, and then the middle y values you end up using twice at some point. The trick is a lot of the free response questions that you'll see with this and with all the other rectangles, they may not always have the same thickness to these shapes. So here we got lucky because it was always 1 for every example, but a lot of times they make some of them 1, some 2, maybe one of them is 3, and you just have to be careful with that. But I need to calculate all of this out. A lot of times these are calculator questions, so I'll quickly do that. And so if we calculate that out, we get 8.417. That's the trapezoid method. And if you look real closely, all of our trapezoids should be slightly above the actual curve, or all the tops of our trapezoids are slightly above. So this is an overestimate again. And so the same question, what would I do to get a better and better and better estimate for this particular method? In the end, the exact value for this, we actually are going to be capable of figuring this out. The exact value is 8.047. That's the actual value, if you just want to jot that down. And in a couple days, you'll be able to figure that out. So, jot down any questions, just 4 very quick examples on how we estimate the area under the curve. We'll do lots of stuff with this in class.